will make life easier for future young researchers, because when I was young, when I was young, I felt, how can I match all the amazing stuff that is done before? And he will give a good explanation. There's unmatchable stuff in the theory of PL. So we'll see how that plays a role, in higher order type level programming Haskell. Enjoy.
Thank you. Thanks. So we've seen today how much fun it is to write type-level programs in Haskell. And in this talk, I'm going to show how to make it even more fun by writing higher-order type-level programs in Haskell. But before doing that, let's go back in time a little bit and quickly recap some of the features of Haskell 98, the language we all know and love. And in particular, I'd like to focus on types in Haskell 98 and type constructors. So we have the int type, which is the type of numbers that can be this type can be inhabited by numbers like 0 and 10. We have type constructors like maybe, which, as you can see from its kind, it's not immediately a type, but it's something that takes a type as an argument and produces a type as a result. And similar to maybe, we have type constructors like either, which take 2 arguments and return a type when provided with 2 arguments. So we can even see this in action. So we can ask GHCI what it thinks the kind of maybe of int is, and indeed it gives us type. Now, these type constructors can be partially applied as well. So when I ask GHC what the type of, what the kind of either of int is, it'll partially apply either to int, and we get back something that has kind type to type. So why is partial application of type constructors useful? Well, as an example, Haskell has this type class called functor, which allows us to abstract over types that have a type parameter, such as maybe an either. And in this case, the functor type class gives us a way to swap out that type parameter with something else. By giving a function a to b, we can go from f of a to f of b. So here are 2 instances for the type constructors we've seen, maybe and either e. And notice that I had to partially apply either here, because normally it takes 2 arguments, and the argument of functor is type to type. So that's good, Haskell 98. How does type inference work? We all know that Haskell has very good type inference, so we expect to be able to just use these functor instances without having to provide any type signatures when we do so. So here's an example of using fmap on a value of type maybe bool. We call fmap show on it, and if we ask what the type of that is, it should be maybe string. So GAC cleverly figured out that going from maybe bool, you can with a function bool to string, we can get to maybe string. So how we did this? Well, a very important thing that GHC does during type inference is application decomposition. So we start out with the type fmap a to b to f of a to f of b, and GHC sees that we passed in a maybe bool as the f of a argument, so it sees that that's an f of a equals maybe bool, and behind the scenes it decomposes this application and discovers that f must be then equal to maybe and a must be equal to bool. So the GHC does this during type inference. As a result of this decomposition, it turns out that all type constructors in GHC are injective. So what that means is we have this function here with a context that says for all a and b, if we know that maybe a equals maybe b, then we can write a function a to b and implement it as the identity function, which is only possible if we somehow in the process manage to learn that a must be equal to b, because the identity function doesn't change the type. So maybe it's injective. And actually, every type constructor in Haskell is injective, so we can even abstract over maybe from the previous example and just say that any f of this kind, type to type, is injective, and this still compiles as we expected. And indeed, if we say we look at the type of injective instantiated with maybe for f, so we can use visible type applications to provide maybe as the argument f. So GHC will indeed tell us that, oh yes, I learned that it must be that a and b must be the same. So all type constructors injective. And all type constructors are also generative, which is the other property of that is implied by application decomposition. So when we saw that f of a equals maybe bool, we learned that a equals bool, which is the injectivity property. But being able to learn that f equals maybe is the generativity property. So in this case, when we know that f of a equals g of b, we can again write the identity function and type it at f of int to g of int, because GAC learned that f must be equal to g. Okay, so this is pretty standard Haskell 98 type inference. So again, just to recap some of these definitions, injectivity means that f of a equals f of b implies a equals b, and generativity in this case means f of a equals g of b implies f equals g. And so when something is both injective and generative, then we can call it matchable, which is a term that characterizes the way type constructors are handled by the type checker. Okay, so let's get back to the future. So far we've been talking about Haskell 98. Now I'm going to, for the rest of the talk, I'm going to talk about Haskell 98, but with a different meaning of the word. That is Haskell with 98 GAC extensions turned on. And in particular, I'm going to focus somewhat on type families, which are just down there at the bottom. So type families are a way of, as we've seen before, type families are a way of expressing computation at the type level in a functional way. So what I mean by that is, if you look at this example, we have a type class here called DB, which is intended to represent types that have a database encoding somehow. So we can see that in the type class DB, there is an associated type family called DB type, which sends a type A into its DB type. So whenever we instantiate in this type class, that we need to provide for every type their DB type representation. There's a function 2DB, which then hopefully does the serialization to the Haskell type, to the database type. So you can see that very similarly to maybe, and either DB type also has a kind type arrow type. So just keep that in mind. So a few examples here taken out of an enterprise Haskell production code base. You can see it's enterprise because username and password are both mapped to plain text in the database. So this is what type family definitions look like, and indeed we can again jump back into GACI and evaluate these type families. This time we put the bang at the end of kind, which tells GACI to really reduce the definitions, and indeed we can see that DB type password reduces to DB text. So we've got a nice type level computation machinery in our hand. But let's just go back to the injectivity property for a second that we've seen. So every type constructor in Haskell is injective, which means that we can instantiate the injective function's f argument with any type constructor, and it'll just work out. It'll know that a must be equal to b because of the context. So in the case of maybe, this worked out. But of course, if we think about the DB type family, this property really doesn't hold true for it, because DB type of username is equal to DB type of password, but we really don't want to be able to learn from that the username is then equal to password. So DB type is not injective, nor it is generative, it turns out. So today in GAC, what happens when we try to instantiate injective, just like we did with maybe? What if we try to instantiate injective with DB type? So we really wish this didn't work. And indeed, GAC tells us that the associated type family DB type should have one argument, but has been given none. So the defense mechanism in GAC is that it simply doesn't allow partial application of type families, because if it did, then we could do nasty things in this way. Okay, type families must then be saturated. This is the rule today in GAC. And in the next couple of minutes, I'm going to show an example where this restriction is really quite restrictive. I'm going to motivate why we really want to do unsaturated application of type families, but let's not get ahead of ourselves. So again, Haskell 98, this is a type level list of So whenever you see a tick, it means that this this constructor is now promoted to the type level. So lists exist at the value level, but tick lists exist at the type level. So the user type is a type level list of these fields that we've seen earlier. So every user has an ID, a username, a password, an email, and some registration date or birth date. Now, in order to have a value that somehow inhabits this shape of data, we can define a heterogeneous list, which is a generalized algebraic data type indexed by a type level list. So what that means is we can have a list whose elements are all of different types, and these types are given by the list. So in this case, we can see that our user Chris is a user which is implemented as a list. Every field has a different type. So what if we wanted to take a user list and turn it somehow into a database list? So again, this is the definition of the user list, and somehow we want to end up with so given this list, we want to end up with a list where every field has been turned into the data type equivalent of the original type. So a function that does this might look like, db user of type agelist user to agelist, and then what? So at this point, we can say, okay, we're just going to hard code the result of this mapping. But the problem with that is that every time then we extend the definition of user, we also have to update the type of the DB user type. So it's kind of unfortunate. What we really want to do is somehow lift this abstraction out and do this in a higher level way. So okay. We can go and define a type family called map, which is the exact same function as map at the value level, but everything has been turned uppercase, which means it's now at the type level. So it goes through a list and applies a function and translates the values. Okay, so we go and say agelist map db type over input over user, and we try to reload, and again, JC tells us that the DB type is partially applied, so that's no good. Sad. Okay, so the first idea, which is due to Richard Eisenberg, is that if we want to keep type inference behave as it already does today, but also do type level partial applications, then we somehow need to distinguish the kind of type constructors and the kind of DB type in a first class way in the type system. So what we're going to do is we keep the kinds of type constructors as they were, but we're going to assign these squiggly arrows as the kind of type families. And so the normal arrow is pronounced a matchable arrow, and the squiggly arrow is pronounced unmatchable arrow for reasons that are hopefully clear by now. So how do we then fix the map function or the type family to accept type families as arguments? Well, we just replace the arrow with a squiggly one with an unmatchable one, and of course, because this is a new feature in GAC, we need to add another extension called unsaturated type families. And I know what you're thinking now. Okay, well, this takes us into Haskell 99 world, and it was already quite difficult to deal with Haskell 98, so it's really no good. But luckily, unsaturated type families implies type families, so we're back to 98, so it's all good, it's all nice. Okay, so right, so we reload in our new version of GAC, enable the extension, and it works out just great. So we can now do type level, higher order programming, and to check the type of this, the type of DB user when applied to Chris is indeed the mapping. So it all works out great. Okay, so as a sanity check, we need to make sure that we didn't break anything in the process. So what happens when we now try to instantiate injective with DB type? Well, previously it didn't work because of the saturation restriction, and now it doesn't work because it's a normal type error, and it says, well, this thing doesn't fit in that hole, so we're still good. Now, what about, so we can now use map to map functions or type families over lists, but we've kind of lost an ability in the process, which is that what if we try to map the maybe type constructor over this list? Well, let's try. Oh, okay, so we get a kind error, which is to be expected because maybe still has the matchable arrow kind, but clearly the kind of map expects a type family. So here's the second idea. Instead of having these two distinct arrows, have only one arrow, which will then be indexed by its matchability. So we have this data type matchability, which can be either matchable or unmatchable. And so now the kind of maybe becomes type arrow, the single arrow with matchability instantiated to matchable to type, and db type to unmatchable type. And I don't know what you're thinking, this looks really ugly. So we can introduce the matchable arrow and an unmatchable arrow as simply type synonyms with the relevant instantiations. Excuse me. So we go back to how things were before, except what this allows us now to do is to go to this arrow and replace it with a matchability variable. So now map is a function that takes either a type constructor or a type family, and let's try map db type user. So in this case, the matchability will be instantiated with unmatchable, and if we do maybe over user, I didn't reload the file. Always reload the file. Okay. And maybe works again. And because I don't have much time left, I'm not going to go into very much detail about how this function works, but just a glimpse of what else you might find in the paper. We can now, using unsaturated type families and some of GHC's more interesting type system features, we can do really nice and reusable generic programming at the type level for the first time. So I can say I want to apply a function everywhere in a type where it can find an int. I want to add 10 to that type level int. So I'm going to just define a type level list of type level tuples of maybes of nats and see what happens. And it adds 10 to them. So if you want to understand this function, go look at the paper. So just to conclude, we just made the type language higher order in a way that type inference remains backwards compatible. We're still doing first order unification. We have an implementation of this work, which can be found at that link. And you can find more details in the paper. Thank you very much.
All right, thank you. I think I was mostly impressed by how long did you practice to get the keystrokes in sync to the video? Okay, never mind. So there's one question online that maybe was answered by the last slides. Is there a subkinding relation between the two kinds of arrows?
Yes. Well, it was. So the answer is the two kinds of arrows are just now instantiations of the single arrow, which is indexed by its matchability. So that's the connection.
Okay, but they're not subkinds of each other, but rather
there's no
subkinds of the polymorphic one.
Oh, there's no subkinding relationship. No.
Yeah. Okay, do we have any real-world person question? Yeah, there.
What's the story with type errors? Do we have to teach beginners about matchable and unmatchable arrows before they can understand things?
Oh, type errors, right. So if you're not using this fancy type system features, then all you're ever going to see is the old normal type error. So the type arrow. So in type errors, you shouldn't see a difference. And if you're already using these advanced features, then good luck.
All right, this must have been one of the clearest talks because there's a surprisingly small number of questions. Oh, yeah, there's one over there.
This kind of looks like an effect system at the type level, right? With polymorphic instantiation. Do you actually ever need the generality of that, or would subkinding or subtyping at the effect level just have been enough?
So you could do subtyping as well, but then you would hit other issues when, so you would sacrifice a lot of the nice type inference that JC does, because subtyping is kind of difficult.
Okay, it just fits better with.
So nearest neighbor?
So in the linear Haskell proposal, we have we have arrows which have little annotations on them that relate to the usage. And this seems like another kind of annotation on the arrow that relates to the usage. Has there been any thought about how to unify these? Is there some sort of, is this just another instantiation of a semi-ring algebra?
Yeah, so this is a very good question, and it's one that we've been dodging for a while. Yeah, there are different proposals, but I don't know if any of them at this point is very satisfactory. So we'll have to wait and see.
Yeah, I think it would be something interesting to look into, sort of going forward, if we're going to sort of forge into some brave new world where we've got these things. Yeah.
Thanks.
All right, I guess everybody's happy to go to the break. So we have a break until in 20 minutes, and then please come back for the student research competition finalist